So today I am going to talk about photoelectric effect. So this is second part of beginning of quantum mechanics. In earlier lectures I talk about black body radiation, and the second part is the photoelectric effect. So let us briefly discuss its history. So Heinrich Hertz in 1887 noticed the photoelectric effect. What he found that a charged object, he noticed that a charged object loses its charge more readily when illuminated by ultraviolet radiation. And Hertz used a spark gap, means two sharp electrodes placed at a small distance. What Hertz used a small a small spark gap, or we can simply say that a spark gap to detect the presence of electromagnetic radiation or the electromagnetic wave. And then he placed this arrangement in the dark box so that things are clearly visible in the dark. After that, he used glass box and increased the spark length and then he reperformed the same experiment with a quartz box and spark length is further increased, and he observed the same effect. And this is called as or this is the first observation of photoelectric effect. Observation of photoelectric effect. Then later, in 1888, W. Halbach confirmed these results. And showed that UV light on zinc plate connected to battery generates current. And this generation is because of electron emission. Because of electron emission. Later, in 1898, J.J. Thomson found that the amount of current varies with the intensity and frequency of radiation. After this, in 1902, Lennard observed that kinetic energy of electron emitted increased with the increase in frequency of radiation. Also, another important thing which is observed important thing was that the emission is instantaneous as radiation fall on the surface. Maxwell's theory was not able to explain this. Maxwell's theory was not able to explain these experimental observations. And the experimental setup proposed by Lennard, it's a complete experiment. So let us have a look at that. So this is the opening. This is cathode. This is a positive terminal, and here it is a negative terminal initially. The terminals and connected across a variable battery or variable power supply. It's a variable power supply. Here microammeter is connected and voltage is measured across it, and here it's like this, right? So this is the experimental arrangement, and light is made to incident through this window on this, and electrons are ejected in this direction. So these are the electrons. So what are the observations? So let us have a look at the observations. So as the intensity of radiation increases, say it is photocurrent, and it is intensity. So as the intensity of the radiation increases, the current will also increases, and it's a straight line curve. Then another observation, say it is the voltage axis. So it is the voltage, sorry, it is at the negative terminal and it is a positive terminal. So if positive potential at this increases, so at a particular intensity, say this is the curve which we are getting. So it is this axis basically represent the potential of this plate. So if it is the zero potential. If potential is zero at this plate, if overall then electrons are also reaching, so it has some value of the photocurrent. But as this potential increases, means this positive potential increases, so that means it is attracting more electrons towards itself. So that means current slowly and steadily increases and the saturation will be reached. And if this polarity is reversed, means if it will become negative, then it keep on decreasing and stage will be reached, then no electron will reach at here, then the current will be zero. So that's what we are observing. So if we are performing same experiment at a particular frequency but at different intensities, then such type of graph we have to obtain. So these are the experimental observations. Here it is I3, it is I2, and it is I1. This represents the intensity. So I3 is greater than this and this, right? So that's what we are observing. And another observations are, say it is photocurrent axis and say it is the voltage axis, is the potential. So at a particular frequency nu1, this was the curve which we will obtain, and if I increase the frequency of the radiation, then same curve we will obtain, but it is slightly here. So here at nu2 the stopping potential will be V02, and here the stopping potential will be V01. Means stopping potential means what? Stopping potential means the negative potential of this plate at which current ceases or current becomes zero. So that's what we are getting here, and say it is the photocurrent axis. So that means at stopping potential, the electron which is ejected with the maximum kinetic energy, it ceases, or it will not reach at the electrode. So that means the energy corresponding to this potential is equivalent to maximum kinetic energy, equals to maximum kinetic energy. And another very interesting graph which we will obtain is that this is the frequency. As we increase the frequency, kinetic energy of the electron, or in other words, we can say that EV0 means stopping potential, it will increases, but the cutoff frequency must be there, means it should be minimum frequency. If it is less than this, then no current will be there, right? So that means there is some cutoff frequency, or the energy corresponding to it is known as the work function of that metal, and it is different for different metals. It is different for different metals. And another observation is that is emission is instantaneous. So these are some observations of the photoelectric effect. So in the next lecture, I will talk about classical interpretation of this and the Einstein's approach to explain the photoelectric effect.